combustion in several angles in the energy industry. When we're talking BPI, Building Performance Institute's view of combustion, we talk more towards safety and combustion safety within a home, because combustion in a typical home or any building appears in many ways. Most people affiliate combustion directly related to heating in the heating appliances, but we also see combustion in your stoves if it's gas-fired, natural gas or propane stoves. We see it in water heaters. We see it in gas fireplaces. We see it in wood stoves and pellet stoves. So combustion is introduced to interior of buildings in many forms for many functions. But we also look at combustion and the energy efficiency arena. Efficiency, and the efficiency of those appliances is primarily related to what we do with the combustion. Okay, so to understand, for me, to understand combustion, whether you're talking safety or you're talking efficiency, you need to understand first what combustion is and what it's all about, because once you understand what combustion is and what it's all about, then you can start really getting into the safety part of it, get into the efficiency part of it. Okay, so first of all, combustion, it's a chemical reaction that takes place. Okay, and it occurs when oxygen, primarily contained in air, all right, reacts with hydrogen and carbon, which is coming to us in the fuels. So we have a couple of different things intersecting here. We have hydrogen and carbon coming into us in a mixture of a fuel, whether it be propane, whether it be oil, whether it be coal. And then we have oxygen coming in as far as air is concerned. We usually introduce that as air. Okay? An element is a pure matter that cannot be broken down. Okay? Anything that's an element, it's a pure matter, cannot be broken down into similar substances. Ignition temperature is an intensity of heat required to start a chemical reaction, whether the chemical reaction, again, is with coal or oil or wood. The ignition source is that intensity of heat that will start the reaction, and the fuel is an oxygen and ignition temperature come together in three in this triangle, if you will, to create what we know as fire. Okay? So when we're looking at fire, when we see fire, we see flames, we know that we have to have all three components. We have to have heat, we have to have an ignition source or an ignition temperature, and we have to have oxygen. If any one of those three items is missing, the fire goes out. Okay? Combustion air, which is what we're primarily going to talk in terms of the oxygen being introduced to the triangle. We talk about combustion air as the oxygen, brings that oxygen to the fuel, okay, for the combustion. The precise amount of air that is dependent on the fuel being used in the equipment, and all heating systems using combustion must have air. So if you put a combustion appliance, and again, this can be a water heater or a heating appliance, into a room and completely seal that room so that the room is airtight, that appliance will not have combustion air, will not have the necessary oxygen to maintain the fire, to maintain combustion. And you'll see in a little bit why that can become a huge issue. All right? So we have to keep that in mind when we're talking about weather-tighting homes and sealing up homes. This is one of the issues that we have to concern ourselves with, because as we go along to stop infiltration from coming into the house, because we don't want to lose our heat, okay, we also have to be concerned with what are we doing to the combustion products or the combustion appliances located in that dwelling. okay, the house or the building. So we have to have a delicate balance here, all right? The oxygen comes from the combustion air that's delivered, and usually it consists of approximately 20.95% or 21% oxygen and about 78% nitrogen is in that air, okay? The nitrogen will go through a fire or go through this, this transition untouched. So when you introduce oxygen to fuel and also the ignition source, and you go into the reaction, which is a flame, nitrogen is what we call a pass-through. It just passes through the flame, does not change state at all. Okay? So if you have X amount of grams, if you have 10 grams, if you will, of nitrogen going into the flame, you're going to have 10 grams exiting the flame and what we call combustion byproduct, or combustion products. And we'll talk about combustion products in a minute. During the combustion, though, the oxygen will react with the elements of the fuel and create the combustion. And the fuel-air ratio for burning natural gas, which is what we usually do most of our discussions on, is with natural gas because it's popular, needs to be about 96 to 86% air, 4 to 14% gas is the ratio, depending on whether you're using an atmospheric burner or you're using a forced air burner. Okay, the ratios will be 96, it should be 86 to 96, and 4% to 14. If we have 4% gas, we consider that a lean fire. And lean being that we have very little gas in the fire. Okay, we have more oxygen than gas, of course. And then 14% is considered a rich flame or a rich fire. So obviously, if you have, if you're running a burner that's running rich at 14%, then its efficiency is probably down because it's utilizing more gas. And that's what you're paying for, is the gas, as opposed to oxygen's free. Okay? The gas is what we pay for. Let's talk about the components for a minute. The ignition temperature can come to us in various ways when we talk about appliances, but it's the chemical, it's the intensity of heat that is needed to start that chemical reaction of taking place, okay? And the chemical reaction is taking place between the fuel and the oxygen. The ignition source is what starts the chemical reaction. It can either be provided by a spark plug type ignition source, it can be a pilot light ignition source, okay? Or any other means. We have glow plug type of ignition sources, so somehow we have to introduce that ignition source. You can have oxygen and you can have fuel residing side by side or even mixed together and have no flame. If you don't have the ignition source, you will have no flame. And we all know that. How do we know that? When do we see that a lot? Anybody know? Kevin? I'm going to pick on you. When do we see fuel and oil, well, spill that out, fuel and oxygen mixed together and it does not fire? Because we're missing an ignition source. You seen that? When we have delayed ignition, anybody have experienced delayed ignition in a furnace, oil fired?
It's not the correct room pressure?
No, it's when we literally have delayed ignition in a boiler or a furnace because for some reason the sparks don't work on the end of the electrodes. And so what happens is the burner turns on, the pump runs, the fan runs, it mixes the oil and the air together, it comes out into the burner, into the fire chamber, and it just sits there. And then all of a sudden, oh yeah, a few minutes later it decides to light and you get that pow, and you hear your furnace rumble, boom, you know. So there's an instance where oxygen and fuel are mixing, they're mixing and they're coming out, but because they don't have the ignition source, they're not firing. So you have to have the ignition source. And the ignition source has to be at a temperature that is at or above the burning temperature, okay, the intensity of heat for that chemical reaction. And it has to be maintained. Now usually the fire will maintain it once it's started, okay? After combustion has started, the temperature must be above that ignition source to keep going. And this is just a picture here of what we typically see as a spark igniter. And we see these on gas grills all the time. You get the little, you hit the button and gives out a spark and igniter. There's another example. You can turn on your gas grill and you got fuel coming out. You got the propane coming out. You have oxygen being mixed in the burner tube between the fuel and the oxygen, but yet you don't have a flame till you hit that button or you light that match. All right. Hopefully you hit it and light it fairly quickly, or else you end up with singed eyebrows. Okay. When we look at flames, we're looking at combustion. And when we look at a gas flame, we kind of talk about gas flames because they're an excellent example of how combustion works. When we look at a gas flame, we have several components. We have 3 components on the gas flame. The first component is what we call the inner mantle. And this is where you have a very rich flame. Okay? We have a very rich flame. The second is the outer mantle. All right? The inner mantle is rich because this is where the hydrogen in the fuel mixture, this is where your hydrogen is burning. All right? Your hydrogen is reacting with your oxygen, and this is where it's burning in the middle of the flame. Your outer mantle is where your carbon is meeting the oxygen and your carbon is burning, because carbon is another product of the fuel. All right? Carbon burns slower than hydrogen. Hydrogen burns very easily, very rapidly. Carbon burns very slowly. So the carbon is in an outer mantle, which is more of a light blue. So when you're looking at a natural gas flame, you'll see the center of the flame, the heart of the flame is deep dark blue. Then you'll have a lighter blue flame surrounding it. And then you'll have the outer tips at the very top that will flash off in a little bit of yellow. Okay? And what that is the unburned particles of carbon. That's the carbon that's kind of made it through the whole reaction untouched. Okay? So it doesn't give off much heat. Your tips, yellow tips don't give off much heat. All right? Your inner and outer mantle, your inner mantle is where the largest source of your heat is, and your outer mantle has the next largest source of heat, and of course your tips has the least. The color and the size of the flame, of course, will depend on the type of fuel being used, all right, and how the combustion air mixes with the fuel, also the type of burner that we're using. We can have natural gas burners that have a whole slew of holes in them over 2 or 3 feet length of a burner tube. We can have small gas burners that are like you see on your cooktop, that are just round. Okay, so we have various types, shapes of burners. The burner face is pretty much where the flame is established on the tip of the flame, on the tip of the burner. All right, and the burner flame usually produces, on a gas-fired burner, mixes the air and the oxygen and the fuel before it enters the burner. So the key here is, on all burners, all types of combustion, the first thing you have to do is mix the air with the fuel. And the better the mix, and you'll see this in another presentation, the better the mix of the air and the fuel, the more efficient the burn is going to be. Okay? So in a natural gas burner, when we talk natural gas burners and talk natural gas combustion, we have the luxury of mixing the air and the gas early on in the burner. And we usually do it in the burner tube. As the gas is exiting the manifold, okay, through the spud and the orifice, and it comes out into the burner tube, we introduce oxygen right behind it, and through Venturi action down the burner tube, the air and the fuel will mix, so that when the fuel and air mixture exits the burner tube to the source of the ignition point where the pilot is, it's very well mixed. Okay? Why do you suppose, and now I don't want you to answer this, Kevin, why do you suppose, and he was eager, why do you suppose that is so? Any guess? Why do you suppose it's mixed extremely well by the time it exits the tube? Think about what is the fuel? Is it a solid? It's a gas. It's vapor. What is the air? It's a vapor. So the two are both in the same state. Vapor state, vapor state, gas state. They can mix very well coming down that tube, and by the time they come out, they're mixed extremely well. Boom. All right? Now, think about this. How many have an oil burner or have experienced oil burners? Okay. What state is the oil? Liquid. What state is the combustion air? Vapor, gas. Now that's a little harder to mix. Okay? Very hard to mix. And that's the function of your burner, okay, your oil-fired burner with the little blower motor on it. Okay, if you're familiar with the construction of an oil burner, it has a blower motor on it because we're injecting air. We have to take that air, blow it down the tube, and then we have to take the oil out of an atomizing nozzle, and we have to break that oil into the smallest pieces and particles that we can. We have to mist it, so to speak, so that it can mix as best as possible with the air. Because now we're trying to mix a liquid and air as opposed to air and air or gas and gas. We're trying to go liquid gas. So oil is trickier to have a good complete combustion. All right. So solid fuels cannot mix as efficiently as vapors or gas fuels. Okay. Burning liquid and solid fuels obviously becomes less efficient, and coal is even harder because it's solid. All right? And that's why coal and fuel oils will produce a white or a yellow flame. So when you look at the natural gas flame, you have that inner and outer mantles that are blue, dark blue and light blue. But when you look at a coal-fired combustion flame, or you look at a coal-fired oil, it's yellow and white. And that is a result of the oxygen not being able to mix 100% with the fuel, as can happen in gas. Okay? Everybody with me? Make sense? All right. Regardless of what we're burning for fuel, okay, what we're mixing together with oxygen, we come out of the fire or the flame with what we call products of combustion, because we're creating a reaction here. We're taking oxygen, we're taking fuel, we're putting them together with an ignition source. They're going through a reaction, okay, and through that reaction, they're going to change. Those two products are going to change, and we're going to call it products of combustion. Complete combustion, if we have complete combustion, which means we burn everything we can out of the fuel, complete combustion will produce carbon dioxide and water vapor. Carbon dioxide is not poisonous. Okay? Incomplete combustion, which means we've left some of the carbon behind, we didn't burn all the carbon in the fuel, will produce carbon monoxide and water vapor. It'll also produce aldehydes, which is very acidic. Okay? So if I have a perfect flame, and we all know that perfection doesn't exist everywhere, but if we had a true perfect flame and I was burning off every bit of carbon introduced into that combustion via the fuel, okay, I would have carbon dioxide exiting as products of combustion along with some water vapor. Everything would be great. I have nothing that's dangerous to concern about. However, because we cannot 100% guarantee that all of the air is going to combine with all of the fuel, especially when we get into oil, trying to mix oil and air, I'm going to leave some carbon behind, which means I am going to produce carbon monoxide with aldehydes coming out, CHO. Okay? So in order to try to achieve complete combustion, we need to have combustion air enough, and we have to know what that combustion air is, for the process or for the burner or the situation. And this is what I was talking about earlier. This is what we go after when we're looking at the efficiency of appliances and how we can change the efficiency of the appliances. We do it through adjusting the combustion air entering the burner. Okay? So complete combustion occurs when enough oxygen is supplied and combined with the fuel. And we can supply the combustion air, enough combustion air, but the other trick is to get it to mix with the fuel. That's the other trick. And again, as we just discussed, you know, your gas fuels, propane, natural gas, are easier, okay, than your fuel oil. So it's, you know, we can have a blower on that number 2 fuel oil burner, and that blower is bringing in enough combustion air, but then the other half of the trick is now that I brought enough air in, I got to get it to mix with the oil. And that's where the other half of the trick is. All right? So in complete combustion, you've got hydrogen, carbon, and oxygen are coming in, they recombine, go through the process, and they form carbon dioxide and water vapor. Again, the nitrogen is just passing through the flame totally untouched. All right? The chemical energy that's in the fuel is changed to thermal energy. That's where we get the heat from. Okay? The reactionary process that takes place in the combustion is what produces the heat. There's no loss or gain of energy because energy cannot be created nor destroyed. All we're doing is transferring it. Okay. Yep.
Where does the nitrogen come from?
In the air. The air, the nitrogen, hydrogen, oxygen. You get some nitrogen, and well, you'd have it. You could have it in the fuel too. You'll get it both. In the gas, you'll get it in the fuel. Okay. So your air is coming in with its oxygen. Your fuel is coming in. This is propane. It's got the hydrogen here. Okay. It's got the carbon. You got your nitrogen coming in down here with the air. So here's your fuel, introducing your hydrogen and your carbon. Here's your air, bringing in your oxygen and your nitrogen. Now, because we said, you know, laws of nature tells us that it cannot be created nor destroyed. So what comes into this reaction has to come out of this reaction, right? Quantity-wise. So what happens is the nitrogen is a pass-through. So for every molecule of nitrogen coming in, we have a molecule of nitrogen coming out. However, dependent on how this oxygen mixes with the propane, which is hydrogen and carbon, and then how it burns off, depends. If we have complete combustion and everything is perfect, then we exit here with carbon dioxide and water vapor, which has some hydrogen, oxygen inside. And it's the quantity, the exiting quantity is identical to the entering quantity. It just changes shape. Okay, it changes shape. So when we look at the air-fuel ratio for this, when we look at, you know, coal, for example, our air quantity per cubic foot is 135 cubic feet per 1 pound of coal we're going to burn. So if we're going to burn coal, for every pound of coal you're burning, you've got to be introducing 135 cubic feet of air to get into that fire to get complete combustion. Okay. Number 2, fuel oil. For every gallon you're burning, you have to be introducing 1,400 cubic feet of air into that fire. Now think about your infiltration. When we're talking about air changes per hour in a home or a building, we're talking about infiltration. If you've got a boiler, an oil-fired boiler or oil-fired furnace in that basement, and the average burner is about 0.75 to 1 gallon per hour nozzle, for every hour it's running, it needs to have 1,400 cubic feet of air entering that fire to be efficient, to be 100% combustion. So when you're sealing the house up and sealing the thing up, you got to keep this in mind. This is something that has to be thought of, because if you don't, you're going to start starving the appliance for air, and it happens. We see it. Yep.
I mean, in that case, couldn't you run like a supply air vent?
Absolutely.
Outside?
Absolutely. This is where you need to bring in outside air, and it's recommended and advisable to bring it in from outside. Okay. Now there's different thoughts of how to bring it in. You can bring it in. Some manufacturers make these jackets that go right on your burner, and you bring it right in raw to the burner, or you can bring it into the room. What I did in my house, I had the situation in our house we built in '96. When we first built it, this is back in '96 now, we weren't really talking about energy. We just built an airtight house. And the first week we were in there, we started seeing the problems immediately. Matter of fact, we moved in day before Thanksgiving. And when we started Thanksgiving Day, we were cooking, had the vent going for the oven, the oven going. And I said, hey, let's build a fire. It's a nice cool day. Let's have a nice fire in the fireplace. So I was anxious to have a fire going in the new house. So went and lit a fire in the fireplace. And then one of the kids went and took a shower, and as soon as they turned the fan on in the bathroom, smoke started coming down the chimney while the fire was going. And we were just pulling in because the house was starving for air. We had it so tight. And then as time went on, I realized because every time the burner would turn on, the thing would just rumble. It would shake and rumble, and realized we were starving the burner for air, and we weren't getting complete combustion in the burner. So in our case, I decided to, in the boiler room, we had a room that the boiler was in, I bought a 6-inch duct, and I brought it in high up in the rafters, and just dumped it into the room high above the furnace. So by the time the air got down to the gun, it would heat up through the natural heat in the room. So I was still introducing room temperature air to the burner. If you pipe it direct to the burner from outside, okay, now you're bringing in, if it's 20 below zero out, or if it's zero outside, which is common, it could be zero outside any time of the night around here in the winter, you're bringing 0-degree air right directly into that fire. Now your flame, your ignition source especially, is trying to combat, that 0-degree air in addition to maintaining flame. All right, so there's two schools of thought on what's the best way to bring it in. I prefer to try to blend the air as it's coming in. As long as the air is available, the burner doesn't know. If you just bring it in the room and bring it up above, the burner doesn't know the difference. What it will know is if it's 0 degrees coming in. That it'll feel. Okay, it'll pick that up. Natural gas is not as bad. Now you see the difference here. Natural gas, you only need 10 cubic feet per 1 cubic foot of fuel burn, all right, and propane is 24, and these are as low as they are because, again, the gas is in a vapor state, and you're mixing air with it, you're mixing, vapor with vapor, so it doesn't need. With the oil, man, you've got to really try to push that oxygen into that oil. So, that's what's happening inside that burner, at the end of that gun, if you will. If you looked at the end of a gun, you go down the burner tube, you got the blower behind you with the oil pump all connected to one, blowing the air down the tube, and the nozzle's at the end of the tube, and if you look at the end, there's a swirl. There's a bunch of, I wish I had one in here. I've got one in the back of my truck. There's louvers on the end to swirl the air, and then the nozzle is designed to atomize the oil as it's coming out in a cone shape. So as the air comes out and swirls, it's getting into that cone nozzle, and it tries its best to mix all of that together and then fire. Immediately try to fire. All right? But the mixture time is very short. The time that the oil and the oxygen try to mix, or the time that it has to mix, is only seconds or milliseconds compared to the way a natural gas burner is set up. The air, the oxygen, and the gas start very early in the tube and mix as it's going down the tube. Well, oil, it's all taking place on the face of the tube. So the time that they're together, and that's why in the oil, we have to introduce far more air for the oil than we do natural gas, because we just have to try to jam it together. You know, we're just trying to whack it together. Okay? So incomplete combustion is improper combustion, of course, that occurs when there's not enough oxygen, which is usually the case. We're starving the fire for oxygen, and we develop incomplete combustion. So when we do that, we're producing carbon monoxide when we have incomplete combustion. And as we all know, carbon monoxide is not healthy for us, not happy for us either. Okay? Very unhealthy for us. And then the aldehydes come out as very acidic, and this is why we'll see, sometimes you'll see, especially on an oil-fired furnace or an oil-fired boiler, at the barometric damper, you'll see this yellowy powder developing on the, you know, with soot on the galvanized pipe, because that's the aldehydes mixing and breaking down the galvanized metal. And that's what's turning yellow, because it's acidic. Okay? The aldehydes contain hydrogen, carbon, and oxygen. They have a harsh odor. If you've ever walked into a house that doesn't have a good flue, you can kind of feel it, taste it, the back of your throat. You know, you kind of go, yeah, kind of metally type taste to it. That's that harsh odor. It'll make your eyes and your nose burn a little bit. Remember, carbon monoxide, you cannot taste it, you cannot feel it, sense it. You start developing symptoms of it. Nauseated, stomachache, sleepiness, headaches. That's all the carbon monoxide. The aldehydes, on the other hand, you can walk in and you can almost taste it on your tongue. Okay? And I've been in homes where you can, as soon as you walk in the door or walk into the basement, you can tell right away, ooh, that's not firing right.
If you can smell it, you should be able to find it too. I should be able to see it somewhere.
Oh, well, yeah. I mean, you should be able to, I mean, if you know, when you smell it, if you know what it is, you know, okay, you got an oil-fired burner. Usually it's from oil-fired burners, more so than natural gas. It takes a lot to get a natural gas flame out of whack to give you enough aldehydes to taste the aldehydes. But oil, very easy. I can starve an oil fire of oxygen real easy. Okay? So the same picture, this time incomplete. Again, we're introducing the fuel, which has the hydrogen and the carbon. We're introducing the air, which has the oxygen, the nitrogen. Again, incomplete combustion, the nitrogen is going to pass right through, 1-for-1 ratio, not change. However, when you look at the mixture of the fuel and the air, now we're going to have a certain amount of aldehydes, which has the hydrogen, a little bit of carbon, and a little bit of oxygen mixed in. Then we're going to have the water vapor, which is obviously hydrogen and oxygen. And then we're going to have a lot of carbon monoxide, which is that carbon component, that yellow flame. That's what's in the yellow flame. That's what's coming out in the yellow, is the carbon monoxide. So when we look at combustion efficiency, we're evaluating the chemical energy, the chemical reaction that takes place. And we're doing that primarily by monitoring the carbon monoxide and the carbon dioxide that comes out of that flame, because that tells us how efficient we're burning. If we're burning extremely efficient, I'm going to see high levels of carbon dioxide. If I'm burning poorly, I'm going to see high levels of carbon monoxide. Okay? So again, when efficiency is high, most of the chemical energy is converted to thermal energy. Because if my efficiency is high, I'm burning all of the carbon content of the fuel that I can possibly burn. If I'm leaving carbon behind, and I'm not burning the carbon, which is producing yellow flame and also producing carbon monoxide, then I'm not going to have as much thermal energy coming out of that reaction as I would if I was burning all of the carbon. Because I'm not burning all of the fuel. The carbon is part of the fuel. Okay? So when we have combustion efficiency low, we're wasting the chemical energy, and we're producing at the same time dangerous products. And those dangerous products obviously can come into the living space or the occupancy space. And if we're exiting those products out the chimney, we're also, this is also what's contributing to global warming. The more carbon monoxide I kick out of here, kick out of there, the more inefficient flame I have coming out, the worse I'm going to be. For hydrogen, the heating value is 61,500 BTUs per pound. For carbon, it's only 14,550 BTUs per pound. So obviously, my hydrogen is giving me the biggest bang for the buck out of my fuel, but I still don't want to leave behind. If I was not burning any of the carbon whatsoever, I'd be leaving behind 14,550 BTUs per pound, which is a lot. Okay, the hydrogen burns rapidly, as we talked about, and very cleanly. Okay, and then carbon burns very slowly. So when we take, when we're looking at fuel and we're looking at combustion, fuel usually consists of 1 pound of hydrogen, or in this example, 1 pound of hydrogen, 1 pound of carbon. Okay, the complete combustion of 1 pound of hydrogen and 8 pounds of carbon, 8 pounds of oxygen is required. All right. The reaction will produce 9 pounds of water vapor, 61,500 BTUs. So again, this is an example of taking 1 pound of hydrogen, 1 pound of carbon, mixing those together. Okay, we're going to produce 61,500 BTUs. For complete combustion of the carbon, we have to have 2 2/3 pounds of oxygen for the carbon alone. The reaction will produce 3 2/3 pounds of carbon dioxide and 14,550 BTUs. Okay, total of the reactants, if we add the carbon, we add these together, we're going to come up to 7050. So again, this example is to illustrate if we're burning incomplete combustion, even incomplete combustion, we're still going to burn all of the hydrogen. Okay? If we're not burning completely, if I had my worst flame, my hydrogen's still going to burn. So in this example, I'm still going to get 61,500 BTUs out of that thing. However, if I burn all of my carbon with the hydrogen, now I'll get 70,050 BTUs. Otherwise, I'm leaving that 14,000 on the table. And that's where we get our efficiency. That's where the efficiency, because you're still buying, when you buy the fuel contains the carbon, so you're still buying all of it. It's what you get out of it. All right? So you can either leave the 14,500 BTUs on the table as far as waste, go up the flue and byproducts, waste byproducts, or you can get the heat out of it. All right? This is what I was trying to talk about earlier. Here's a picture of it. So here, this is your typical number 2 fuel oil burner. You've got a motor here driving your fuel pump and your blower, squirrel cage blower. It's driving the air down this tube, but the air that is driving down that tube doesn't mix with the oil until it exits the tube right at the oil nozzle. And that oil nozzle develops a cone mist of oil, takes your solid oil, of course, puts it under about 125 pounds pressure off the top of those pumps. That's what they run at. All right, and with that pressurized oil, it's putting it through that atomizing nozzle, turns it into small little tiny droplets of oil, as small as it can be, and then the air is exiting those little fins, and it creates a swirl. So it swirls with the oil, and it tries to mix that oil and air. But it's doing it right at the ignition source. I got you. Hold on. It's doing it right at the ignition source, which is right at the very tip. You have 2 electrodes at 10,000 volts, sparking away there, creating the ignition source. So all of this is happening right at the end. Where if this was a natural gas burner, the air and the fuel can mix way deep in the burner tube, and by the time it exits the burner tube, it's very well mixed because it had more time to work together. Yep.
Now, on like a system that has like a bigger load, would it change the size of like the nozzle?
Oh, absolutely, absolutely.
For different,
I mean, how many BTUs per gallon of oil?
139, I think.
139,000. Okay, some books will say 140. All right, so if my heating load is larger than that, if I have to have 150,000, then I got to go up beyond. So when you look at these nozzles, they're rated in gallons, in angles, okay, and whether they're hollow or solid cone. All right, so the average home is 0.75 to 1. So you're either you're about 75,000 BTUs, 140,000 BTUs, depending on what the setup is. Yeah. Somebody else had a question? No. All right. So if you have that nozzle, when we look at those nozzles, you can for every hour that boiler is going to run, that's what you're burning for a rate of fuel.
Now over time, not everything's going to get burnt. Do those nozzles ever like gunk up?
Oh yeah.
And then create less efficiency?
And that's exactly what we do. If you're a service technician, that when you hire them for your yearly cleaning, that's one of the things they do is they usually change the nozzle. It's cheaper than dunking them in kerosene. I've done it before. You try to dunk them in kerosene, blow them out, clean them. But for the price of the nozzle, you might as well just change it out. You swap it out, and then likewise your fuel filter. Yep. And this swirl, this swirl right here where the air is, those will also fill up with dust. If you have this burner, if your burner is in your basement and so is your clothes dryer, that thing will be full. Every year I used to pull hours at our other house because it was in the room. It was in a room here, and our washer and dryer was here, and that thing would be plugged right up solid, so it wasn't swirling the air. It was just kind of blowing the air in, and that'll drastically affect. Okay, so how we do that, how we know that is, and I'll show you this in a minute, I'll pass it around. We use a combustion analyzer where we go in and we sample the combustion products and see what we're getting for combustion products, and it tells us where our efficiency is. And that's how we can tell, what's happening in this flame. All right. So we've talked about this, how the carbon burns slowly, and if we don't get enough, if we don't get enough oxygen, the carbon won't burn at all. And a telltale sign of you exiting carbon is soot. And if you can tell even before you pull your analyzer out, if you walk into the basement of a home and you're looking at especially an oil-fired appliance, whether it be a water heater or a furnace, and you see soot, black soot all around the rings of the elbows and whatnot, on the breeching, on the flue, you can tell right off that there's a lot of carbon coming off of that flame, because carbon will produce soot. Just like a candle, when you see a candle burning, okay, the candle and the wax, and you see the black soot coming up, that's all carbon. It's all carbon coming out. So a telltale sign without the instruments is just look for the evidence. Look for the soot, look for that yellow powder created by the aldehydes. All right. Sometimes if it's bad enough, and I've seen this, you can stand outside and look at what's exiting the chimney. If you see black smoke coming out of the chimney of an oil-fired appliance, you're really burning bad. You shouldn't see visible smoke. You might see, don't mistake smoke for steam. Okay? You may see white steam, that's common. But if you see black smoke coming out of a chimney on an oil-fired furnace or boiler, you're really burning bad. You're burning real bad. Okay? Convection currents along the draft will carry these unburned particles. That's what we were talking about. So away from the flame, okay? And of course, the further away from the flame you get below the ignition source, and the carbon won't burn. And then what happens is, and what we don't measure when we're doing all this testing, is this soot will develop on the inside of the heat exchangers of the boiler, or the heat exchanger of the furnace, and then it'll insulate. Soot has an insulating value to it, and it'll insulate the heat exchanger from the flue gases. Now, a lot of people believe that when they're looking at their burner, they're looking at their furnace, their boiler, they think that the flame is heating the water or the air. and it's not. It's the flue gas that we depend on. Because we're operating flue gases around 300-400 degrees Fahrenheit, and that we're extracting that heat from the flue gas into the medium, whether it's air or water, that we're using to heat the building. Now, if the soot builds up on the inside of that heat exchanger where we're trying to extract that temperature of the flue gas out, now it slows down the thermal transfer, and we all know what R values does to you, right? Okay, so it's creating an R value in that black soot, and that's even giving you worse efficiency out of the appliance that you won't measure. This will tell you, if we go in with a combustion analyzer, this will tell me how efficient the fire is, but it won't tell me how efficient the appliance overall is. So if the appliance has soot built up in the heat exchanger, this cannot measure that. This will not tell us that. So this is where this is where good maintenance of the appliance comes into play. Because if you just go in, you measure your, let's say the thing has been operating for over a year now inefficiently and producing a lot of soot, and that's a condition we call sooted. It's sooted up the inside of the furnace. If I come in and just adjust the flame and make the flame run more efficient, but I don't get rid of the soot, I didn't gain a whole lot. I gained a little, but not a lot. I got to clean the soot out to get it all, to gain my most efficiency. So this is where you'll see, if you've ever seen the service technicians come in, after the, first thing they do is just take the thing apart, and they take their brushes out, and they brush down the inside and vacuum it all out. They're getting all the soot out. That's what they're doing. They're taking the soot off of the heat exchanger, and once they get it cleaned up, then they'll go in and adjust the flame and get it running. Question?
When the soot builds up on the heat exchanger and it reduce the efficiency, will say in a boiler, will it take longer for the water to heat up, or will the system recognize it and push more fuel in?
No, well, the system won't. That nozzle's fixed, unless you have. We do have some boilers that will sense outdoor temperature and inside temperature, and it'll adjust flame for that. But we don't have anything really that it senses and says, hey, you sooted up, okay? Burn higher because you sooted up, okay? So no, usually they're fixed. So for maximum efficiency, 5 to 50% excess air is required for combustion, and this is something that we get into when we're dealing with how much air to bring in. We call it excess air is the term we use for combustion air coming in. All right. Too much air can also rob you from efficiency as well, because if we bring in too much air, we're going to just draft everything right up the flue. So it's one of those things where you have to have just right. You can't just say, all right, you said enough. I'll just blow this thing with all the air I can. Too much air is too much air. Too much air will just take the heat and rob the heat exchanger of the heat that it needs to pass through to the home. Okay, so we do efficiency testing by measuring the flue gases. We also measure how much oxygen is coming out of the gas. Okay. We measure excess air going into the flame. We measure the percentage of carbon dioxide in the gas, because that'll tell us. Recommended levels for carbon dioxide if you're dealing with a natural gas fire burner is 8 to 9.5%, so we'll measure for that. Recommended carbon dioxide levels for number 2 fuel oil is anywhere from 10 to 12.5%. I'm going to pass this around. What we do is we take, this device has a pump on it, and the pump literally sucks air right out of the flue. We inject this into the flue. Okay. Oh, was it fitting a little loose? So we drill, if it's not already there, we drill a 1/4-inch hole in the flue. We position this probe into the flue till it reaches its highest temperature, so that we know we're positioned right, and all this is just a little slide so you can hold it there. you know, once you find that sweet spot, if you will, the high temperature spot, you just adjust it so you don't have to constantly move, you can just lean on it. And then when we turn this on, come on, there it goes. When we turn this on, you'll hear a pump kick in. You can barely hear the pump, and it's drafting, it's drawing air in. This thing, and most of these today will do this for you, it'll give you all the information you need right out of the gate, okay? In other words, it'll calculate your efficiency for you directly. All you have to do is punch in what you know, whether you got number 2 fuel, or you have natural gas, or you have propane. There's no calculating. The older units, you used to have to go to some slide rules and charts and everything else. So, you know, this has a water trap on it, so it'll prevent water from getting into the instrument. That's all that does, because we are pulling out some vapor, water vapor in the flue, from the flue. So it's pretty simple to use. Wait for it to get through the warm-up cycle. When you pass around, you'll see, and I'm hoping I have one stored on here. It's warming up. Okay, so when you look at this, the first thing you'll see on the display is you'll see, you know, it tells you what fuel you want to pick, and then if you hit the button again, it gives you, you know, natural gas number 2, number 4, number 6, propane, kerosene, wood. This will do wood. Coal, and that's about it. So I guess wood pellets would be wood. If you know, wood pellets is the biggest thing. And then I'm going to leave it on the third page, which shows you the different readouts. You have your O2, your CO, your efficiency, and your CO2. Gives it to you all automatically. Calculates it for you. You don't have to sit there and calculate your efficiency. It'll tell you exactly what your efficiency is. It'll also give you your stack temperature, your entering air temperature. Okay, so I'll leave it on that page so you can see the typical, you know, typical readout. So this is what we're doing. Again, is we're analyzing through the products of combustion, because that's what tells us how complete combustion is. Okay, it's, you know, it's pretty simple there. And this just talks about how these are used. And in the United States, we are responsible for 24% of the car, and maybe this is higher now. This may be old data. 24% of the carbon monoxide emissions from fossil fuels from our country. So we're, you know, so you think about this for, you know, next time you're driving down the road, hopefully you're looking at houses differently today than you used to, you know. And, you know, when you're driving down the road, and if you're looking at chimneys and you see black smoke coming out of those chimneys, and especially if you see oil pipes on the side of the house, you know right away it's oil feeding that house. You know, we're feeding carbon monoxide into the atmosphere. For all that black smoke, that's all carbon monoxide going into the atmosphere. Okay? All right? All right, I'm not going to give you homework. Next year you'll have it. Let me show you. Any questions? Okay, I have this.
I have a question.
Sure.
Approximately how much air does a wood stove hold, do you know?
I don't have that on my head, Wes, but I know we have it in our book. If you look at the book, the heating book, we have it for wood. How many? We have all that in there for wood. This is an incomplete presentation I have, so we'll muddle through it a little bit. And I'm going to be honest, this is some of Wes's material I took and mixed it around. And remember, you sent me over that PowerPoint presentation there that you had. Okay, so this is talking about how, a little bit more detail on how we do this testing. We test some of the things we test for fuel pressure coming in. We're going to test for draft. Draft is important because we can have an overdrafting situation which will give us excess air. If we're pulling too much air through the burning appliance, we're pulling way too much air across the flame, and you know, we're going to have that same situation I talked about earlier. We never measure for smoke. We don't do any smoke testing on propane or natural gas because it doesn't produce smoke. We don't get a lot of smoke out of it. However, oil, because oil and coal produce a lot of smoke, especially wood, because of the carbon content, this will not test for smoke. We use a smoke tester, which is it's a long handheld vacuum you put in, and you draw a sample of air, and it draws it through a white screen, and then we pull the white screen and we compare it to a chart, and it tells us what the percentage of smoke is. And you'll see that in this example. As we talked about, we test for monoxide, dioxide, and excess air. So this is typical atmospheric forced hot air natural gas system. It's an atmospheric burner, which means it has no power vent going into the burner. Okay? And in this case here, this is your flue going up to your chimney. We put a 1/4-inch hole, as I talked about. We have to insert this probe into that draft, so we drill a 1/4-inch hole right on the top here. We also take our stack temperature readings right off the top on this type of appliance. We'll take our stack readings right as we come out of the breeching. Okay? And then, of course, you can measure the efficiency. Also, we can calculate efficiency, and we did this in the heating class last week with your temperature rise of your air entering and exiting the appliance in itself. We won't get into that here. Okay? So, what's required for combustion is primary and secondary air, and then what we call excess air. This is natural gas. This, again, is what we call an atmospheric burner. And in an atmospheric burner, we introduce primary air, okay, into the burner tube. This is what I was talking earlier. And then we introduce secondary air around the burner tube at the face of the burner tube here. So your primary air and your natural gas is mixing the whole entire time that it's traveling down that tube. So in this situation, not only is the oxygen in the same state as the fuel, they're both in a gas state, and they have that luxury of mixing, they also have the luxury of having a lot of time to do it, traveling down this tube. And then they also have the ability to introduce secondary or excess air around the tube. So you get a real good mixture with gas, propane, LP, okay, natural gas. And then we have our reaction taking place right here, where our ignition source will be. The flue gases, that's where our reaction takes place. Then the flue gases are going to come up through this area where it's extracting the heat from the flue gases to heat the air. And then it's going to start heading up the flue. So we're going to be measuring here and here with that meter that just went around the room. That's where we take our measurements. So we call this dilution. When this mixes, when the oxygen mixes with the fuel, we call it dilution. All right? You have fuel coming in, air coming in. Incomplete combustion will give us carbon monoxide. Okay? If we have complete combustion, we get carbon dioxide. And you can see the nitrogen is going to pass right through untouched, and the hydrogen is going to burn. Okay? So combustion efficiency is based on how much energy is in the fuel, as we calculated in the earlier slides. It'll depend what the net stack temperature is, because again, we're extracting the heat out of that combustion gas. That's where we're getting the heat. We're not getting it from the flame. We're depending on the flame to produce the hot combustion gases, which is where we extract the heat. And then we look at the percent of oxygen and O2 in the flue gas. Okay, and again, just different examples where we're looking. Okay. It's only accurate when your oxygen stack temperature and your CO readings are within manufacturer specifications. So you have to have an idea. Even so, this is calibrated for standard equipment. and we have all kinds of chart for standard equipment, but you always, whenever possible, you should always be referring to the manufacturer's specifications. And we see that it'll either be stamped on the appliance, or it'll be found in the nomenclature you get with the appliance when you buy the appliance. Okay? Then we have to make sure we're taking our readings once the stack temperature is stabilized, because you're going to have what we call run-up. And run-up is the time that it takes for a cold appliance to sit there and start on a cold start and then come up to temperature. So you kind of have to turn the appliance on, watch your stack temperature, and wait for it to equalize, wait for it to reach and stabilize. Once it stabilizes, and then this is a typical readout. You just saw, you just saw it with blank numbers, but this was an example done with number 2 fuel oil, had a stack temperature of 302, an ambient room temperature of 59.5, so your overall temperature, your rise, is going to be 302 minus 59.5, because you're starting at 59.5 degrees. You can't count that. That's the air coming in. And that's why I was saying there's two schools of thought here. If you're going to introduce 0 degree air, 100% outside air at 0 degrees, now you would take